This podcast is brought to you by LMU Munich.
Good afternoon. Welcome in the honored summer for the Trade Center for Theoretical Physics. It's great to see so many people here around. Of course, it's my great pleasure and even greater honor to introduce the speaker of this colloquium, namely Professor Shing Tung Yau from Harvard University. As most of you know, Professor Yau is one of the most important and greatest mathematicians alive. His work had significant impact both in mathematics but also in physics, and hence I think he is the most suitable speaker for this joint colloquium as in mathematics and physics. Professor Yau originates from China. He was born in Shangtung. Then he obtained his first degree at the Chinese University of Hong Kong, where I think he lived also for some time. And then, at the age of already 22, he received his doctoral degree at the University of California in Berkeley. His doctoral advisor was Shing Tung Yau, another very famous mathematician. Then he spent several years at the Institute for Advanced Study at Princeton, at Stony Brook, at Stanford, and other places, and since 1987, he has been professor at Harvard University. Moreover, Professor Yau is very much committed to develop mathematics in China, where he established various research institutes, most notably the Munich Center of Mathematics in Beijing, which was established, I think, in the year 1996. He was also the main organizer of the String Conference 2006 in Beijing, where I also had the pleasure to be, and it was really a fantastic event, I must say. Professor Yau's work, as I have mentioned already, had a wide influence in geometric analysis. Probably his most famous contribution is the proof of the Calabi conjecture, namely, in short, that Kähler manifolds with further class are Ricci flat. These spaces are therefore called Calabi-Yau manifolds. They are, of course, very important for mathematics and general relativity, but Calabi-Yau spaces are also of utmost importance and interest in string theory as they describe solutions of the string equations of motion. We, as string theorists, are using the Calabi-Yau spaces every day. It is, so to say, our daily mathematical bread and butter. The second very important contribution is the proof of a long-standing conjecture, namely that the total mass in general relativity is positive, a theorem that implies that flat space-time is stable. This is certainly not only relevant for us string theorists, but I think it's also relevant in daily life. Professor Yau did also major contributions to mirror symmetry, and I think he is constantly interested in string theory, as we also could encounter in the discussions of this morning. Professor Yau received numerous prizes and honors and honorary degrees. I have counted at least 23, and for his outstanding work he received the Fields Medal in the year 1982. So, Professor Yau, we are very happy and honored that you are here in Munich, and we would like to thank you very much for your visit. Before we start, let me remind you that today's talk will be followed by the colloquium tomorrow in the Mass Department at 5 p.m. about quasi-local mass in general relativity. Now we are very glad to hear your talk about the shape of space and time. And by the way, there's a very nice book written by Professor Yau, which I think is written in English, which you can buy. So welcome here in Munich. We are very happy to have you. Thank you.
Well, thank you very much indeed. It's a great honor for me to come to Munich to give this talk. I have many friends here, and I've discussed with string theory this morning and this afternoon. The work is really impressive for me. I'm a geometer, but I work with physicists for the last 40 years. I look at physics from the point of view of geometry, and it's very fascinating to me. So that's why the book and the topic is called The Shape of Space-Time, or The Shape of Inner Space. So I will discuss my understanding of space-time, the geometry of it, how it is relevant to physics at the end. And some of them well known to some people here. I bet your patience to listen to that. So I was a student in Berkeley, and the first major interest for me was geometry, Riemannian geometry. The concept of geometry had gone through a drastic change in the 19th century, thanks to two great German mathematicians, Gauss and Riemann. It's a spectacular work due to Riemann to understand what curvature means for two-dimensional surface. He always tried to generalize it. Then his student Riemann actually did the job. And this really revolutionized our notion of space, freeing the concept of both mathematicians and physicists later. So no more linear space or surfaces in free space are the only notion of space, but also something which is curved. So objects no longer had to be confined to a flat linear space as we see it in Euclidean geometry. He proposed a much more abstract concept of space of any possible dimension, and where we can describe distance and curvature. And the curvature is one of the very, very major reasons why Riemann and Gauss want to understand. So it can be done on such an abstract space. And we can do calculus over such a space. And this becomes a very important development in the middle of 19th century. Riemann actually visits Italy quite often. He has many disciples there, including Richard, Bianchi, and several other people. And these people, as a group, has developed a foundation for the Riemannian geometry. And this extremely fruitful concept. And of course, this is all done by Riemann, I think, when he was 30s. For a long time, Riemannian geometry was considered to be abstract nonsense. And no people know why the geometers care about it, because it's abstract space and you never see it. Until 50 years later, Einstein developed the general relativity, the theory of general relativity. And he found out that this kind of geometry, which involved curved space, was exactly what he needed to unify Newtonian gravity with special relativity. In fact, of course, we know that in 1905 he has already developed special relativity with help from many people, including Poincaré. But in 1908 he was trying to understand how to unify gravity with special relativity, which was inconsistent at the time. Until 1912, he understood the potential of gravity cannot be described by a scalar function. He understood it by thought experiment, and then he asked his friend Grossman what kind of thing was that. And so then geometry comes in, Riemannian geometry. But in any case, geometry, topology, and partial differential equations are the major branches of mathematics that provide a major link to understand space-time. Here, geometry, I include subjects related to algebraic geometry and group representation theory, along with the intuition based on physical principles such as general relativity or string theory. These few important subjects of mathematics really give beautiful description of the universe, which what makes me fascinating as a dependent geometer, because nothing is more beautiful than nature. A very important tool for understanding the interaction between topology and geometry actually comes from analysis. And a large part of my work actually was based on these partial differential equations. The power of these linear elliptic equations already can be seen from the application of the index field formula due to Atiyah-Singer in the 1960s. And a lot of important computation in quantum field theory was based on the index formula. But that's more linear theory. The large-scale structure of the universe actually are nonlinear. And because they are curvature, once you have curvature, they are nonlinear. And the large-scale development of nonlinear theory has to start only around the 70s. And the subject is called geometric analysis. So many of my friends and my students have been devote themselves to understand and develop this major branch of geometry called geometric analysis, where we use nonlinear theory to study geometric objects. And for the last 40 years, my own research has been understanding the relation between topology and curvature. So topology is a global structure of the space where we don't care too much about distance and curvature alone. But curvature is geometry, part of geometry. How the global structure of the topology linked to curvature has been a very important concept for me. And as such, I found that my work has been somewhat interesting to my friends in the physics department, because it turns out many of the important questions can be formulated by this relation between topology and curvature. In fact, already in the index formula is already a relation between topology and curvature. Anyway, so let's come back to general relativity. Well, we already know special relativity says space and time should not be treated separately, but should instead be merged together to form what we call space-time. And Einstein, as I said, had a big struggle to understand the fundamental description of gravity. He got help from his friend Marshall Grossman. So he asked Marshall Grossman, instead of a scalar, what kind of things can be used to describe gravity if it changes according to direction and all that. So Grossman suggests the tensor, and I think Grossman did not know much about geometry at the beginning. So he went to the library, he found the great works by Riemann and Gauss, majorly Riemann, and Richard later. So he suggests to Einstein these are the major framework that he should use for gravity. So they wrote a joint paper in 1913 together. So it was accomplished in 1915 by Einstein. So Riemann provided a framework of abstract space and as well as how to define distance and curvature. And this is important for Einstein. And he also drew the important work of Richard, who defined a special kind of curvature that could be used to describe the distribution of matter in space-time. So Richard defined some part of the curvature, not a full curvature. Curvature tensor is a big tensor involving 4 indices, and Richard just take the trace of it. So it's a small part of the curvature tensor, and yet it satisfies a very important rule, namely the law of conservation law holds on Richard tensor. And this is very remarkable, and Einstein captured that and used Richard tensor to describe the distribution of matter in space-time. That becomes the Einstein equation. So the left-hand side of the Einstein equation consists of Richard curvature, take off the trace in order to satisfy the conservation law. So this is exactly the right law in order to provide a geometric picture of gravity. So from then on, rather than consider gravity as an attractive force between massive objects, it could instead be thought of as the consequence of the curvature of space-time. So the curvature of the space-time tells you how matter distributes and how gravity performs itself. This is the curvature of space-time, not the massive object itself. Well, actually, it's kind of interesting to look at what Einstein wrote about it himself. He said, since the gravitational field is determined by the configuration of masses and changes with it, the geometric structure of the space is also depending on the physical factors. Thus, according to this theory, space is, exactly as Riemann guessed, no longer absolute. Its structure depends on the physical physical influences. So space-time is changing, according to time also. And geometry is no longer as isolated, self-contained space like the geometry of Euclid. So it's no more static. It is moving dynamically. And Riemannian geometry provides the exact framework. So he wrote, after he finished his whole work, he said, in the light of the knowledge attained, the happy achievement seems almost a matter of course, because he said after he found it, any intelligent student can grasp it without too much trouble. You can write it down once you understand it, as usual. But the years of anxious searching in the dark, with their intensive longing, their alternation of confidence and exhaustion, and the final emergence into the light, only those who have experienced it can understand that. So often a true theory takes a lot of work before you finally understand it, although at the end it looks quite simple. Anyway, the critical contribution of Riemannian geometry has been one of the major struggles he went through, because he needs to understand Riemannian geometry before, it was obscure subject before. Now, when I was a graduate student in Berkeley, I studied general relativity, not extensively, but I learned the equation of Einstein. And I was fascinated by the fact that in the Einstein equation, the matter only controls part of the curvature of space-time, because matter is equivalent to Ricci tensor, as I told you, and the Ricci tensor is only part of the curvature of space-time. So I wonder what happens if it's not there, so when it's vacuum. So the space-time is vacuum, and the Ricci curvature is identical zero. Could we still have curvature, or could we still have gravity? So that was a question I was curious about, namely a space-time with no matter at all, and yet there's still gravity. Well, such a space does exist. The famous Schwarzschild solution to the Einstein equation is such an example. The matter tensor is identical zero, and it describes a black hole, static black hole. And so it satisfies these conditions, and it has non-trivial mass because of the gravity. On the other hand, this universe, as was described by Schwarzschild, has a singularity. There exists a point where all the law of physics broke down. So that's a point in the center of the black hole. And as a geometer, I was not too happy with such a point. So, well, I guess many physicists are not happy with that point, and many physicists try to cure this singularity, because you still want to make sure you can understand law of physics everywhere. Anyway, so I'm interested, therefore, as a graduate student, to find smooth space without singularity. And to make things more important, the gravity to be more important, I want the space to be compact and closed. So no boundary and curve up as a compact object. And that's different from Schwarzschild solution, where it is open and extended space. So the question for me then becomes, could there be a compact space that contains no matter? So the Ricci curvature would be identical zero. It would be a closed vacuum universe where the force of gravity is still non-trivial. So the gravity or the full curvature tensor is not trivial. I was rather fascinated by this question because I thought it's not obvious. And at that point in 1971, the prevailing intuition of geometry is that such a space should not exist. And indeed, I do not believe it exists, and I try very hard to prove that because I think this would be a beautiful freedom in geometry, that such a space does not exist. Well, when I started to think about this problem in the early 70s, I did not realize that Eugene Calabi had already posed almost exactly the same question way before me. I was reading books in the library, I found this problem. And, but Calabi framed the problem in more complicated mathematics language, which involved concepts like Kähler manifold, Ricci curvature, and Chern classes. It has nothing to do with physics, it sounds like, at that point. But it is interesting because the whole statement can be framed in terms of Einstein's theory of general relativity. He basically adds some more information, namely he put some concept or complex structure over it, or nowadays is you want a space should admit some kind of internal symmetry called supersymmetry. So I do not know what supersymmetry means, those terms at all in those days, but I know what complex structure means. So this is a fascinating question because in this context, the Calabi question actually is exactly the same question that I was curious about, except you add supersymmetry. But the question that Calabi asked is far more systematic and far more accessible than abstractly thinking about the question, because Kähler manifold or supersymmetric space provide a systematic way to construct those spaces that I was interested in. So give a systematic way to find a compact universe with no matter and yet has gravity. So because we could not even find one, and Professor Calabi said that there are many more. So we thought this cannot be true. We thought it's too good to be true. In fact, many of the young geometers at that time, some of them are big famous names now, including Nacho Hitchen, who was a good friend of mine. And we were working very hard to try to demonstrate Calabi was wrong. The reason it's too good to be true is that not only there was not a single example we know of, and yet Mr. Calabi suggests a systematic way to find it. And there it becomes, once you found it, you proved what he said is true, you found many, many more examples. And this is unbelievable in those days. So we could not, on the other hand, we tried very hard. We could not give any evidence that it do not exist. And in fact, I even announced a counterexample in 1973 in a big geometry conference in Stanford, where a few hundred people, geometers, were there. And a serious gap was found afterwards. After I announced the proof, after a few months, Calabi wrote to me and said that there was some question I'd like to ask you. Then I know immediately that there's a problem. In fact, I tried very hard to answer it. It was not communicated by email, so I have 2 weeks to think about how to reply. I tried extremely hard and come up with many, many interesting arguments, very delicate arguments, and working so hard without practically no sleep. And I found that each time I found a possible counterexample, I found a subtle reason why it could not work, the counterexample. After many, many such attempts, I conclude that the conjecture cannot, must have some truth to it. Because each time when I found a counterexample, it broke down in a very delicate manner. I conclude that nature cannot fool me in such a bad manner, that there's some truth to it. So after I make up my mind, I switch gears completely and put in all the energy to prove it's right. Now this is not easy because that was not a time where people understand, geometers understand nonlinear equations, and the people in nonlinear equation does not understand geometry. So I have to actually build a framework, build the right tool in order to prove this conjecture. So it takes 3 more years working very hard with many friends together, build a necessary framework, and finally I achieved the proof in 1976. So that was a really happy incident for me because I worked so hard for it. But let me mention, in the same Stanford conference, I was in a talk given by Robert Garros, who is a general relativist from Chicago. He literally challenged all the geometers during the conference. He said, well, there's this problem, it's called the positive mass conjecture, which says that the total mass or energy in any isolated physical system must be positive. I should not say close, so isolated physical system. So you take a bunch of galaxies far, far away from here, the total mass you observe should be positive. And it's important to have this problem because you want to make sure the physical system under gravity, under general relativity is stable. If you have negative mass, the whole space-time could collapse. So we don't like that to happen. So this was finally proved by Rick Stern and myself in 1978. This was quite an ordeal actually involving minimal surface. So I was looking at all these things from point of view of geometry. I used minimal surface and using all kinds of works from geometry. Although later, Ed Witten provided a new proof which is more consistent with what physicists like to think about. But on the other hand, I should say that the method we brought in is rather new to people working in general relativity, so they were somewhat surprised by us using different methods. But conversely, I should say that the full statement of the positive mass conjecture surprised me a great deal. Because when I look at it from the point of view of geometry, I don't believe that it's true. It's only because the physicists said that it's true, I said maybe these guys cannot be fools, so there must be some reason to it. So finally we proved it based on geometry only. And so this is a really interesting interaction because I would not think I would come up with a statement like that just based on geometry. And yet the physicists actually have been working on this for many, many years. And they could not come up with proof. And so from the point of view of geometry, I did come up with proof, but I don't know the statement of the statement. So this experience led me to think more about general relativity as a subject in physics. At the beginning, I know nothing about general relativity, but I was working on this, I know more about what's going on. So we proved some more things about formation of black holes and clarify the concept of mass of general space, which I will talk about tomorrow actually, this concept of mass. But in any case, it was fascinating to work with physicists. And this, we come up, this statement, we come up by a completely geometrical view, which is interesting. So we proved that if in a region, if the matter density is large, related to radius of the domain, then a black hole must form. So this basically says that in a region when the matter is getting denser and denser, the space-time will collapse and the black hole will form. Now this, of course, you read it everywhere when they talk about black hole. So when they say matter start to condense, black hole will form. Now notice that this independent state of the matter, for any matter whatsoever, as long as the matter density is large, bigger than this concrete number 4 pi squared over 3r squared, then a black hole will form. So this scale is similar to say that when you go to a neutron star, if the density is getting about maybe 1 or 2 times heavier than the neutron star, the density, then it has no way except to collapse to a black hole. So, so this we proved by pure geometry, and it's still one of the best theorem in geometry. Actually, it could be formed in terms of problem in geometry. So, as I found that really satisfactory to work with the physicists, get some understanding. As I said, on the other hand, this statement is completely motivated by geometry. So I've been interacting with many friends in general relativity, and it makes me open to collaborating with physicists in the development of string theory later on. Although this come much later, it come in 1984. When I was working in general relativity, it was in 1978. But when I proved the Calabi conjecture, I found it fascinating because I found a general mechanism to construct space, which nowadays called Calabi-Yau space. And this actually has been extremely useful tool for mathematics. So independent of string theory, this space has been a powerful structure to understand some old problems in geometry. And that's why I actually got a Fields Medal based on this space, way before the string theory became popular. But in any case, at that point, I had a strong sense that somehow this is a beautiful piece of mathematics. And as such, I felt it must be relevant to physics and to our deepest understanding of nature. However, this space is not Lorentzian signature, so it's difficult to see exactly how the idea may fit in. And I do not know enough physics at the time also. But I have friends, because my activities in general relativity. In 1981, I hired Gary Horowitz as my postdoc. Actually, with the major reason is the understanding general relativity. He was actually a student of Garros. And then Andy Strominger came as a postdoc in the physics School of Natural Science in the Institute for Advanced Study in Princeton. So both of them were my friends. So we talked about things together a lot. But then, after I was leaving the institute, and I was in San Diego, one day when I was watching the blue ocean, I got a call from them. They were very excited about a space-time, a model describing the vacuum state of the universe, based on a new theory called string theory. So I know nothing about string theory, and they were very excited about it. They told me the string theory is built on the assumption that particle in its most basic level make of vibrating bits of string and phases that come up. In order for this theory to be consistent with quantum mechanics, and they introduced supersymmetry, a concept, a certain symmetry called supersymmetry. And based on that, space-time is forced to be 10-dimensional. So this was the basic assumption from string theory that, and also the supersymmetry, that force you to have this 10-dimensional space-time. So they told me about it, and I was not sure whether they agree or not, these things. But they really excited about it, so they want to know exactly what I can prove, because I told them roughly what I could do, and they were not so sure. So they believed that this space will play an important role in string theory, and as they were endowed with the right kind of supersymmetry. And so, to their delight, I told them the statement they want is exactly what I could prove in 1976. So they were very happy about it. Then, also, I got a phone call from Ed Witten, who I knew a year before, because he provided new proof of the positive mass conjecture, a beautiful proof. Then he told me that this is one of the most exciting eras in theoretical physics, just like those days when quantum mechanics was being developed. And he was trying to encourage me to get into string theory. He said, well, you may not have anything to do with physics, but if you work on it, you would. So I was looking into it after that. So he collaborated with Candelas, Philip Candelas, Horowitz, and Strominger together. They wrote a famous paper in 1984. And they were looking on the geometry of the 6-dimensional space using a mechanism called Kolisek-Klein model. So what they want to say is that the 6-dimensional space will curve up into a very, very small space, and they call this Krabbe space. The other four-dimensional space could be just the one in general relativity or the space-time as we see it, the Minkowski space-time, 3+1 flat space-time. So that was what they proposed. And the large spatial dimension as we see it is, of course, just like in this room, we have x coordinate, y coordinate, z coordinate, and putting time on, there's four-dimensional space-time. The six-dimensional time is extra, is very tiny, and this invisible space exists at every point in the real space, in the four-dimensional space, and they exist there independent of each other. That's why it add up to be 10-dimensional. So according to string theory, it's like the Planck scale, you cannot see it. Now, the existence of this extra-dimensional space is fantastic, but on the other hand, the shape or the geometry of this six-dimensional space-time does dictate some properties of the universe or the kind of physics we see, because it tells you the particle nature from the geometry. In fact, this Krabbe space we call inner space, and it's the title of the book that I wrote. It's called Shape of Inner Space. So let's see how it works. I mean, so it determines the kind of particles that exist, the mass and the ways in which they interact in the four-dimensional space-time. So the way it goes is that you try to study the spectrum of the Dirac operator on the 10-dimensional space-time. But now you see the 10-dimensional space-time is a product of a 6-dimensional space and the 3+1 space-time. So you take the principal separation of variable on the 10-dimensional space-time. There will be the spectrum of the Krabbe space would contribute to the spectrum of the 10-dimensional space-time for the Dirac operator. Now, so the Dirac operator on Krabbe space can be identified without much problem. Those with non-trivial eigenvalue turns out to be describe those particles which are too heavy in mass, because we are assuming the diameter of the Krabbe space to be very small. By scaling, the spectrum would be too large, and so therefore it will be so large that you cannot see it. So the only thing left that you can see from the Krabbe space are those where the spectrum is equal to 0. And so when the spectrum is equal to 0, it turns out the Dirac operator is completely described by harmonic forms, what we call, and these are described by the topology of the Krabbe space. So the topology of Krabbe space dictates the 0 part of the kernel of the Dirac operator of sitting on the Krabbe space, and which contributes to the operator on the 10-dimensional space-time. So that's how the topology of the Krabbe space contributes to the particle content of the 10-dimensional space-time, which is supposed to be seen in nature. So these are interesting because not only the mass and all this can be calculated once you know the topology, but also the interaction between them. So it's really marvelous because when Einstein said that the phenomenon of gravity is really a manifestation of geometry, string theory boldly proclaimed that the physics of nature can be computed in terms of geometry. That's the reason why the string theory is anxious to find the precise geometry of the 6-dimensional space. Unfortunately, this is still a problem that we are working on, and it's far more complicated than what it was thought at the beginning. And for example, in 1984, Witten was very eager to learn more about Krabbe space. At that point, it's probably fair to say that he knows very little about algebraic geometry. Now he probably knows more than me. He flew from Princeton to San Diego, I was in San Diego, to talk with me about how to construct such a space. When the string theory just began, it was thought there were only 2 Krabbe space. And then when he came, I construct many of them by hand in the order of 10,000. And he was not too happy about it, but on the other hand, we have to face the reality. that there are many more things that we have to deal with. So now, of course, it has grown much more. That's why we have this whole field landscape and all that. But still, how to understand the totality of all this space is still a mystery in geometry and in physics. And so this is rather interesting to me, but it is a challenging job. The number turns out to be large, but I would hope that the number is actually finite. And this is by itself already a challenging, major challenging question for algebraic geometers. It's still not known to be true. But my view is that it should be finite. But if we can prove that it's finite, the method of proving it's finite should lead to a way to classify them. If we can classify them, then I think a lot of problems in physics that puzzles of physicists could be understood much better. At least we have a list of them, and then we can talk about them. Right now, we don't even have a list of all of them. We just found a large number of them, and what they are, we can calculate, but not sure whether we have exhausted all the possibilities. Anyway, the excitement about this space, as like in many subjects in physics, it started to die after a few years. And, but then there was excitement suddenly appeared in the 1988, 89, when Brian Greene, Professor Philip Candelas, and others began to explore the notion of mirror symmetry. And this was interesting. It appears originally from the subject of conformal field theory, and they were able to realize those questions more geometrically. And this is really a turning point for many geometers or mathematicians to try to look at the whole subject. At the very beginning, there are only a few mathematicians who care about the subject, but now there are many, many more. So the proposal was that there are two different Calabi-Yau spaces. They could have different topology like here, and they seem to have nothing in common, and yet they would give rise to the same physics. The quantum field theory associated to it could be the same. So that was a relationship which was completely new to mathematicians. In fact, Brian Greene was my postdoc at the time. He came in to tell me this phenomenon, which I said that doesn't sound right to me. Well, because I don't know enough physics and about conformal field theory. So until when what they have constructed is exhibit some interesting phenomena, we are very much convinced by what happens. So this actually becomes extremely powerful in the hands of mathematicians nowadays. So basically what happens is that just like in physics, because two Calabi-Yau spaces are the same, one turns out to be easier to handle by perturbation theory, and the other one is strong coupling and could not be easily handled. So one can solve a problem in one Calabi-Yau by perturbation analysis, and the other one will be isomorphic, so it will be fine. So this, in particular, makes a great contribution to mathematics problems of counting curves that had defied resolution for a long time. So these are curves counting that appeared about 100 years ago, and this turns out to be called an instanton for one of the models in the Calabi-Yau space, quantum field theory. So it turns out the mirror symmetry argument was able to provide a way to count it. This, in the old days, about a century ago, this is called enumerative geometry, how to count such a thing. And we don't even have a formula to count it in the old days, so let me give you a way to do it. So this is called mirror symmetry. It's a duality. It tells you how to count rational curves of various degrees. And so let's give you an example of what happens. Then you understand the history better. There's a German mathematician called Hermann Schubert. That's about end of 18th century, 19th century, I mean. And they want to count the degree 1 polynomial, rational polynomials, inside a bigger surface, which now is called Calabi-Yau. It's a quintic, it's a degree 5 polynomial. He found that degree 1 subpolynomial is exactly this number, 20x75. So he did it by brute force, where he developed something called supercalculus. Only in 1986, after that many years, Sheldon Katz found degree 2 examples. So there's a large number, 609250. So then around 1989, 2 Norwegian mathematicians were able to compute degree 3 curves. Now, at the time when they compute this number, it's a huge number, as you see. And it's not computed by hand anymore, it's computed by computer. Well, first of all, you develop some machinery, and then you use a computer program to help. So this was a big number. And just look at these numbers, you have no idea what the formula would be. So n equal to 1, n equal to 2, n equal to 3. But you have no idea what it looks like. So at the point when Miller symmetry was developed, Candelas and his group found that degree 3 should be this number, different from the previous number. See, the previous number is this number, found by 2 Norwegian geometers. And Candelas found this number. And then there was a big controversy because mathematicians do not believe physics at all, because the kind of idea that physics put up is kind of based on intuition, physical intuition, which is cannot be proved, and in a rigorous manner. It's an intuition based on conformal field theory and all that. So no people believe in this number until after 3 months. The mathematician found that the programming has a mistake. And this was a fantastic incident, because there's a huge debate, and then it comes down to finding an error in the computer code. And after they correct the code, it turns out to be exactly the same number. Now, of course, the number is not come up by accident that easily, because it's a big number. It's not a small number, like number 2 or number 3. It's a huge number. And turns out to be exactly the same. Now, so what happens is that the counting is rather delicate, and the formula was provided by the string theorists by a non-trivial formula based on Miller symmetry. And the formula up to now cannot be derived otherwise except by this motivation. But the formula, on the other hand, can be proved by different means. And this was finally proved in about 5 years later by Giventhal and Leung and Liu and myself. So the proof was completely different from the original argument, and it's a completely rigorous proof that is based on algebraic geometry and all that. So what does that mean? In an indirect manner, we prove the physical intuition provided by string theory are accurate. Now remember, this formula provides a huge number of numbers. I show it to you, n equal to 1, n equal to 2, n equal to 3, but there's a prediction for n equal to 4, etc. And this turns out to be right and can be proved. So you would say that mathematics provide a laboratory to give some way to prove the intuition provided by physics are okay. Now I want to say that the argument that we provide here depends on the knowledge of the formula. In other words, if we don't know the formula already there, we would not be able to produce the proof. So it's really a collaborative research. Knowing the formula coming from Candelas and other people on the Miller symmetry, based on that formula, we prove it. And so going back based on this proof, we know the formula makes sense, and therefore the physical intuition that they provide is reasonable. Although one cannot say is accurate until you have an experiment. So far this discussion of meter symmetry is on the true level of perturbation because these are all curve of genius zero, no handle. So in the perturbative quantum field theory, these are true level. Now there's high loop contributions which corresponding curves or high genius with many handles now. So I've been counting rational curve. Rational curve are curve with genius zero, so there's true level. But one would like to look at high genius, and this becomes a far more complicated subject, and up to now we still don't understand it completely. So what happens is that given Calabi-Yau space, you can associate a quantum field theory called sigma model. These are the space of maps from the surfaces into the manifold. And these are the traces of the string that vibrate in space-time. And turns out, because of symmetry here, internal symmetry here, you can associate two superconformal field theory, some kind of quantum field theory that means supersymmetry and scale invariant. And because they are obtained by certain twisting, one is called A model and the other one is called B model. And the correlation function associated to this quantum field theory is for A model counts the algebraic curves in the Calabi-Yau manifold. So for rational curve, for curve high genius. And this kind of quantity is now pretty well understood by mathematicians. It's called the Gromov-Witten invariant. And this appears in the classical, in the quantum correlation to the classical correlation function in the A model. So in one of the quantum field theory, we associate such things and we know what they are. But then there's a B model. The B model is proposed related to the proposal given by four physicists, B, C, O, V here. So Wafa is my colleague, and when he proposed this, I was rather fascinated by it, although I don't understand a single word of what he's talking about, because he's thinking about some mathematical formula and letting something go into infinity without justification at all. But in any case, it was obtained by quantization of something called Kodaira Spencer field gravity. The high genius contribution to this field is supposed to be the partition function of the B model, which is a meter symmetry of the original one. So there's A model and B model, and supposed to help you to count the high genius curves. And counting high genius curve is also a very important mathematical question. That's why we are interested in it. And these are actually a subject that mathematician knows almost nothing about also. So recently, a mathematician called Costello and my student Seeley in his PhD thesis formulate a mathematical theory of perturbative quantization of Kodaira-Spencer gauge theory. So these are rigorous formulation, far more rigorous than the BCOV formulation. And they formulate it so that it can be understood in terms of something called obstruction theory. And it turns out they were able to carry out this whole theory, which was originally extremely complicated, at least when the Calabi-Yau space is one dimension. So you may be curious why such a big deal. But the whole quantum theory behind it is totally non-trivial, even its elliptic curve, one dimension. And Seeley, my student, in his thesis was able to verify the whole theory, meter symmetry, to be true for all genius, for not just in tree level, but for all level, all loops. And this is rather remarkable. This is the first time that meter symmetry was proven for all cases for this single manifold, the elliptic curve. The counting of the contribution is actually very interesting. It is involves a lot of number theory calculation involving modular forms, and turns out two completely different theories comes up with the same answer. It's rather remarkable fact they involve huge amount of identities, which is not clear before. So this was a one development on mirror symmetry, which is already, I think, is marvelous. In the other direction, mirror symmetry was, at the beginning, was majorly based on conformal field theory, more algebraic. It's a rather mysterious concept for geometers. So in 1996, Schrödinger, myself, and my postdoc, Saslo, were given a more geometric understanding of this whole theory. So basically, we found out that it's basically something called T-duality. So what does that mean? What it means is that we decompose the Calabi-Yau manifold by two subclasses of three-dimensional submanifold. This is a six-dimensional manifold. We decompose it into two subclasses of three-dimensional submanifold. One of the class will consist of a toroid, so the product of three circles. On the product of three circles, we can perform an operation which is called duality, and similar to operation like mapping a circle of radius r to a circle of radius 1 over r. You can generalize this one a little bit more by duality, but anyways, basically you invert the circle to a big circle. And once you do it, you can put the Calabi-Yau space together and form a new Calabi-Yau space, and that's the mirror of the old Calabi-Yau. So that was our geometric intuition that provides what mirror symmetry goes. And this, of course, is rather different from the original work of conformal field theory. And this whole thing is called, nowadays called SYC construction. It's compatible with some other construction. This is rather interesting and has been developed into on its own sake by many algebraic geometers. So there's Mark Gross and Siebert, a German mathematician. They have given a formulation of this in terms of algebraic geometry. So the subject now is being taken on its own life in mathematics by algebraic geometers and become a very powerful subject, all based on string theory, based on understanding of an important concept of mirror symmetry. There are many, many important developments that I could have mentioned, but let me not mention it. So over the years, some really extremely interesting and powerful mathematics are inspired by string theory. This is mirror symmetry is only one of them. And the formula developed through this connection has proven to be correct. And this is independent whether experimental physics can prove string theory or not. We simply prove it by abstract, rigorous reasoning. And will always remain so. So this is great. But of course, string theory still stands as the only consistent theory that unifies the different forces. It's beautiful theory, and it's interesting. Instead of unifying the different forces of nature, it has unexpectedly led to the unification of different areas of mathematics that at one time seems to be totally unrelated. So the geometry, differential geometry, algebraic geometry, representation theory, and even number theory has been kind of unified under the theme of string theory. That was a marvelous incident that was unexpected before. Of course, we don't know what the final work would be, but we can see, on the other hand, in the past 2,000 years, the concept of geometry has evolved over several important stages. From Euclid to calculus, the invention of calculus, to Riemann, and then to the modern days of string theory. Each time when geometry was transformed, we see physics transformed, and vice versa, when physics was transformed, we see geometry was transformed. So it's fascinating, and of course, I think many of us expect there will be a new geometry that will be evolved in the 21st century, something called quantum geometry, and nobody knows what it means, except it should incorporate quantum physics in the small and general relativity in the large. That was, of course, a great thing if one can do anything like that. And, well, the fact that, that abstract mathematics can reveal so much about nature is something I found it both mysterious and fascinating. As I said, a lot of things that I did is based on intuition in geometry only, and that turns out to be useful for some reason, which I found out very mysterious. So the mathematics produced by string field is so beautiful that it has branched out in many different areas, makes you wonder whether the physicists might be onto something after all, even though it may not be found in experiments so far. But anyway, I found out this whole story is fascinating, and I'm proud that, or lucky to say that I've been part of some of this development, and I hope will stay to be involved in the effort for as long as I can contribute. Thank you.
Yeah, thank you very much, Professor Yau, for this beautiful talk showing us this great relations between mathematics and physics. So there's, I think, time for questions. Please. Andre?
What is the most beautiful part of your work? What do you think is the most beautiful part
Oh, what?
of your work?
Well, constructing Claudius space is most beautiful because it come out of the blue to me also. And as I said, many times I was discouraged that I cannot prove it, or I thought it was wrong. And then finally come out to be right. And you look at the Ritchie metric up to now, we still cannot construct it, not even by computer. And yet you can prove by abstract reasoning that it's there. So I found it very fascinating.
Please ask some questions or comments.
Yeah.
The Lobby's equations, he had always in mind, and always he didn't have feeling spirits. He didn't have superstition. So what was the motivation?
The original conjecture was based purely on Kähler geometry. Claudius' thesis was on Kähler geometry, and at the beginning, I think Claudius only cared about Kähler geometry. And the reason that he motivates it is nothing to do with physics, nothing to do with holonomy. I think at the time when he developed it, the concept of holonomy is not so clear. And the point is that the first Chern class is represented by Ritchie curvature alone. And that by itself is a beautiful concept. So he has looked at that. So first Chern class is represented by Ritchie curvature. If the Ritchie curvature is equal to 0, the first Chern class has to be 0. So I think he does look at it this way.
Is there any other question? Also, not experts, of course.
Yeah, I never really understood why one thinks that these additional 6 dimensions have to be curled up in a very small kind of thing. What would happen if it were large?
I mean, first of all, there will be many more particles that you may not see. You should have seen it if you did not see.
Okay, if the other dimensions are larger, then we would see more particles in our coordinate.
Well, I just described it there. The spectrum of the Dirac operator for the 6th dimension will show up if it's not is big.
So we have an upper bound for the size of these. So what is that?
Well, I thought at one point people thought 1 millimeter or something like that probably should be much smaller.
It depends, it's about 1 inverse TV or so, because the LHC is now testing the energy region. If there would be new particles, one would see that also with the LHC. So the energy or mass scale, you can translate into the length distance. It's set by collider experiment, basically.
Yeah.
You first talked about isolated universes, which are in the ground reference here.
Right.
Does the Calabi-Yau manifolds represent such compact universe?
Yeah, it's the 10 dimension. It's part of the 10 dimension. Calabi-Yau space is 6 dimension, poured up with the Minkowski space-time, which is 12. So the 10 dimension space-time is the vacuum state.
Yes.
In string theory, Calabi-Yau manifolds rises the fluxless in the compactification case. Now, if you also allow for fluxes and you have to relax this condition, you consider generalized Calabi-Yau geometries or any other more general geometries. So, what is your view of treating Calabi-Yau manifolds as sort of special case in a more general context?
Well, as probably know, I work on it also. I construct some models. They're nice to be able to work on it, and they're non-trivial mathematics also. But I think they're less beautiful, less elegant, and less simple compared to Calabi-Yau mathematics. Well, later, of course, I did not mention, for gauge theory, the work that I did with Ken Moon that on constructed Hermitian mills, I think that's elegant and simple. So it's possible that Calabi-Yau coupled with the Hermitian mills are natural. But putting flux so far, at least from the point of view of mathematics, doesn't show enough simplicity for me.
Any more questions?
Yeah.
When these Calabi-Yau manifolds represent isolated universes, I didn't get the argumentation why these are acting on the bigger, on our universe. Why is that?
I'm not coupling with cosmology. I'm just talking with Calabi-Yau for simple models. I mean, for the model we see global. We are not coupling cosmology where the cosmology space-time is changing. We are just taking the maximum symmetry. The space-time has maximum symmetry.
I think the question is why Calabi-Yau space influenced the physics before dimension.
Yes, because we talked about the topologics of these Calabi-Yau manifolds influence on the.
Well, as I said, the Dirac operator coming from the Calabi-Yau has meaning from topology because the spectrum is trivial, then they are exactly described by the topology of the Calabi-Yau. And they are contributing to some part of the spectrum of the 10-dimensional space-time. And this part will give some particle physics for the whole universe. That's how it comes out. It's this part. The contribution to the kernel of the Dirac operator, and that gives rise to particle quantum.
Well, I think there are no more questions. Professor Yau is also around tomorrow,
right.
So if you want to meet him, I think you can do so in the math department. So for today, let me thank you very much again for your talk.